So I thought this all fancy last time. You know, we looked at the pre-abelian group on the set A cross B. We had a subgroup that was defined by elements of a certain form. It's basically designed to give us relations in the quotient. Tensor product was this free group mod A. Practically speaking, this is, what does a garden variety element of this look like? Well, it looks like a sum of tensors. And finite sums, of course, that's what a typical element looks like. Subject to some relations here. A1 plus A2 tensor B is A1 tensor B plus A2 tensor B. There's that. And A tensor B1 plus B2 is A tensor B1 plus A tensor B2. And 3 R times the tensor, or A tensor B, is RA tensor B, plus, or which is equal to A tensor R. Now, last time when I wrote this relation down, I put R's in front of it. This last relation says that I can basically absorb that into the tensor if you like. Okay, so this is what the tensor product is, right? Some consequences. In A tensor B, 0 tensor B equals A tensor 0 equals 0 tensor 0, which is equal to the 0 element. So, for example, I told you all to sort of think about how to do this last time. Well, here I'm going to represent Z2 as 0 bar, 1 bar, like that. Anything in here is a sum of tensors, right? Because that's what elements of tensor product look like. Now, lucky us, I can kind of enumerate this here because there's only 4 tensors, right? I've got 0 tensor 0, bars are 0 tensor 1, 1 tensor 0, and 1 tensor 1. But there's not actually 4 tensors because 3 of these are the same. These are all 0 tensor 0. So at this point, I know this is isomorphic to one of 2 things, right? Because remember, this is a Z module, so it's an abelian group, right? And that's that. This is the group of either one thing or 2 things, right? And the only question is this a non-zero element of the tensor product? And actually, you can sort of, I encourage you to kind of like just do the hand computation and verify that this is not 0 element. This is isomorphic to Z2. We'll get actually a result in a bit that shows that this is isomorphic to Z2. In fact, you might exercise. Let n be the natural numbers. Well, actually, you could even have up to 1. Yeah. So it's natural numbers. So this is just kind of an exercise fun. Anybody want to guess what that is? GCD. Great guess. Yeah, fantastic. For D is the GCD. And I want to give you some theorems here that will help you verify that is in fact the case. So let me give you kind of the first path on understanding the tensor product a little bit from the point of view of homomorphisms. This is once again a famous universal mapping property that it has. So theorem, and I'm going to tell you kind of the real power of this one. Get this written down. 683. Suppose that A, B, and C are R modules. A, B, C, D, R modules. And I guess I'm going to call it F is, or no, G. A cross B to C is a bilinear map. So remember, this is something that's linear in the other variable. When you fix one variable, it's linear in the other. Then there exists a unique R module homomorphism. We call it G bar from the tensor product of A and B to C, such that G bar iota equals G, where I mentioned that iota earlier. No, let's do that here. Where iota well, actually, where iota from A cross B to the tensor product given by iota A comma B is A tensor B is the canonical bilinear map. What is more, here's the universal part. A tensor B is uniquely determined. Up to isomorphism by this property. So let me draw you a diagram of this. So here's the situation. So this is part of the magic of tensor product. So what you have here is you have a bilinear map. And bilinear maps are usually easier to construct than homomorphisms, especially from the tensor product. And here's the other piece that you have. You have this canonical bilinear map. And I'm going to try to convince you really quickly that this is in fact bilinear. What this theorem says is basically tensor product allows you to turn this G, which is bilinear, into an honest to goodness R module homomorphism. Such that when you do iota and the G, it's the same thing as G. This is very powerful, right? Here's one of the reasons this is powerful. Suppose I just walk up to you on the street and give you a tensor product of A tensor B, and you want to make a homomorphism from A tensor B into some other module A tensor C. What's the first difficulty that you're going to encounter here? Well, remember, how did we build the tensor product, right? When we first got our tools out and built the thing, it was a free group modulo some subgroup that gave it certain relations, right? That means that the first thing you're going to have to do with everything is you're going to have to prove to me that that function, whatever you say it is well defined, right? And of course, if you look back at that example that I did earlier in class, what did I do? When we looked at Z2 tensor Z2, we had 4 tensors in there. And I don't know about you all, but it's not readily apparent at this point that the 1 tensor 1 is not the 0 tensor, right? How do you know that that's not in there, right? So there's all kinds of problems with this. If I just try to build this just in the raw, then I've got to worry about well-defined. I mean, I don't even know which tensors represent 0. There's difficulties here. 99.9% of the time, whenever I have to build a homomorphism from a tensor product somewhere, this is what I use. I start with a bilinear map and lift it here, because the bilinear is easy to verify, and this theorem, it's magic, tells you that this you can turn that into a homomorphism. So that's part of the power of this. And the tensor product is the unique solution to this mapping problem. It's determined uniquely up to isomorphism. Okay, so let's prove this. Let's let F be the free abelian group. Oh, actually, before I do this, let me before I stampede off, let me note first that if you look at iota of A1 plus A2B, this is A1 plus A2 tensor B, which is of course the way that this function is defined. And this is A1 tensor B plus A2 tensor B, because tensors are set up to follow that rule. And this is iota A1 comma B plus iota A2 comma B. The proof that it's linear in the second coordinate when you freeze the first is the same. And also notice that R, iota, etc. So in particular, this iota, as promised, is bilinear. Okay, so now let F be free abelian on set A cross B, and we're going to let K be the subgroup that we define when we define the tensor product. So it's generated by elements of the form A1 comma A2, A1 plus A2 comma B minus A1 comma B minus A2 comma B, etc. Those ones when I first defined this. The map E from A cross B to C bilinear by assumption. So this induces a homomorphism F is free. This induces a homomorphism that I will associate with G, which I'll call G star from F C. Because remember, a free abelian group is a free Z module, right? And this is one of the big things we learned about free things. What do I mean by it induces a homomorphism? Well, everything in F is a linear combination over Z, Z linear combination of ordered pairs from A and B, right? All you have to do is tell those ordered pairs A and B where to go in C, and that gives you a homomorphism, right? Because remember, any free object, if you tell its generators where to go, or if you tell its basis where to go, that determines the homomorphism. And that's all we're doing here. The way this works is it just sends the basis elements to where G does, right? And it expands it linearly. So that's your homomorphism, right? That's induced by G. Since G is bilinear, every element of K goes to 0. Under this assignment. Because, for example, you have A1 plus A2 B minus A1B that's what a typical generator of K looks like. Well, let me reiterate, that's one of the forms of the typical generator of A. Now, if you apply G to this, notice that this gives 0, right? So that's what that statement means. And so in particular, what that means is, so K, the subgroup generated by this and the other forms of the elements contained in the kernel of G star. So G star induces. So this is an isomorphism theorem. This is actually the general statement of the first isomorphism theorem. This induces G bar from F mod K. C. So G is our induced homomorphism. And all you have to do is just follow the G's here. If you do G bar and iota, and there we go. The only thing really to remain here at this point, so there is an induced homomorphism. The only thing that you need to really do here is convince yourself that this is an orthogonal homomorphism. But that's pretty straightforward. Now, I did say uniqueness, so if H from A tensor B, C is another such homomorphism. Of course, I want to show that this H is the same thing that you get. This coincides with G bar. And the way I want to do this is I'm going to show that H and G bar actually agree on tensors. So notice that H of A tensor B. So when you do H on A tensor B, since it agrees with the other one, it should agree with G of A comma B, which is G bar of A tensor B. Because this G is G iota, which is this thing. So H and G at same value on each tensor. That is, they have the same value on each individual tensor. So H and G are the same on each sum of tensors. So H and G are the same. Okay. Any questions on that? So I'm going to show you actually how to do some of this. So this is actually going to come up in a couple of theorems that we do, actually applying this theorem. In fact, here's the first place that I'm going to do it, correlating. Suppose that A prime B prime, somebody else, B R mod, oh, that's it. R modules. And suppose we have R module homomorphisms. A prime and G from B prime R module homomorphism. Then there is a unique homomorphism. There is this unique R module homomorphism. From A tensor B to A prime tensor. And I'm going to give this a suggested name actually. F tensor G, such that Raleigh. This is often called the homomorphism induced by F and G. Right. Notice that I did not describe the complete homomorphism. I only described what it is on tensors, right? But again, if I understand what any homomorphism does on all tensors, then I understand what it does everywhere, right? Because the tensors, even though everything in here is not a single tensor necessarily, everything in there is generated by tensors. So let's prove this. So this is kind of the first look at how I like to use this math problem. So my burden is to get from here to here, right? And here I have across me. Look at my pretty picture. Right now, what I want to do is go from here to here. I need this. So I need me some bilinear G business going on here. How should I define this bilinear map? I guess I'm going to take AB. Oh, someone help me. Remember, this is math. Okay, there you go. F of A tensor U. So my input is an ordered pair here. My output is a tensor. Now let me do a quick verification that this is in fact a bilinear map, which I will call G here. Let's verify that that's actually bilinear. Notice that, and again, I'll do kind of half ones on the one. So notice that G of A1 plus A2 B is by definition F of A1 plus A2 tensor G of B.
We use another letter for the max because you already have a G.
Oh, I really should, shouldn't I? Let's do that. Let's call this H. Sorry about that. But let's call that H. Okay, so by definition, this is tensor product under F of the first, tensor G of the second. Right? Now, by assumption, these are both R module homomorphisms, so I can spread those out. This is F of A1 plus F of A2 tensor B. But of course, it is tensor time in the big cities, right? So this is F of A1 tensor B plus F of A2 tensor B, which is, by definition, H of A1B plus H of A2B.
Like times GP and not P.
Oh, I'm sorry. Yeah, I just completely freaked out. Yes. Thank you. That should be G. That should be right there, and that last line's long. Everybody okay? Okay, so linearity in the second variable is the exact same proof, just replace the A's with B's. Let's just check really quick the scale multiplication. So if you look at H of RAB, this is F of RA tensor G of B. But again, I can pull the R out front. Right, because F is an R module homomorphism. And I can write this way. Oh, and this should be G. This should be R F of A tensor G of B. And this is R H of AB. And of course, I can also move this R into the second chord and put it in so it works there as well. All right. So everybody convinced that's bilinear math, that H is bilinear math. Okay, well, our previous theorem gives us there exists H bar in fact, there exists unique H bar from A tensor B into A prime tensor B prime. And we'll see such that, and of course, I'm going to just dub this F tensor G, but we want to verify that this happens. Well, notice that H bar of A tensor B. Actually, it might help me go back to my diagram here. Let's see what happens here. H bar of A tensor B. I want to know where this goes over here. Well, notice that this actually comes from the order pair, right? And by the fact that the diagram commutes, H bar of A tensor B should be H of, yeah, that's right, H of AB, which is F of A tensor G of B. This should be H of AB. Just after writing. Insert here. And I think I got all the bases covered that you need, R module homomorphism. And the only thing else is that my notational convention is instead of calling this H bar, I'm going to call this a tensor G. Okay. Any questions on that? Right. Let me I want to do this out of order. I don't know why I'll put this off so long, but I'll do this. Let me do another one of these, kind of help us warm up a bit. Okay, any questions on this? Okay, so I'm gonna freak out and skip up a couple of theorems and I'm gonna come back. Just because I think these theorems are kind of more in keeping with this. Theorem. And this will be useful as an application later. Let A be then anybody won't guess this.
Okay.
Correct. So when you tensor an R module with itself, I sort of think of a tensor just canceling this size point today. This is another nice application of the universal mapping property of the tensor product. But this one, we got to go a step further because I didn't just give the existence of a homomorphism that does something. I want this to be an isomorphism. So I'm going to show one-to-one and onto. So that's going to be interesting. How is the universal mapping problem going to help us there? Well, the first thing I want is I want a homomorphism I want to get there. So I want to do the bilinear thing here. Actually, I wish I could use the other word, but it didn't matter. Here, the bilinear map takes the ordered pair AR to a tensor R. How about a bilinear map? Oh, there you go. How about that? So I'm going to call this. I'll call this. This actually sort of helps with my scalar multiplication. It's fairly easy to see that this is a bilinear map because if you look at G of A1 plus A2R, this is R A1 plus A2, which is RA1 plus RA2, which is G of A1 R plus G of A2 R. Additionally, G of A R1 R2 is R1 plus R2 A, which is R1A plus R2A, which is G of A R1, G A R2. And finally, now let S be a scalar from R. G, well, let's say SG of AR is SRA, which is let's say SRA, which is G of ASR. Or you can write this as let's say R SA, right, which is SA, well, G of SAR. So this thing is a bilinear map, right? It allows you to kind of do a map that's sort of multiplying the element R times A. The bilinearity does nicely for you here. Okay, so using our theorem again, we now have, let's say, G bar from A tensor R into A. And I can tell you what this does on tensors. Everybody okay with that? Now, here's the difficulty. We need to show that G bar is bijective, right? Because I did say isomorphism. Can somebody justify the fact that G is onto? That's the easy.
One.
Okay.
Great.
Easy peasy lemon squeezy on that one. Now, 1-to-1 is harder in this case. And not surprising, right? Really, because A tensor R, I mean, at the end of the day, the construction that you make A tensor R from might have crazy cosets, strange relations, or whatever. It turns out to be as easy as A, but we don't know that at this point. How am I going to show that G bar is 1-to-1?
I have a question. So are we always assuming from now on that R has an M? R has
You
one?
bet, you bet. That'll for sure be my default.
Okay.
Yeah. Other questions? Okay, how do we show this 1-to-1? This is a hard problem in general. But if there's something about this particular tensor product that allows me to do a little prestidigitation. Let's suppose let X be in the kernel of G bar. And of course, what I want to do is I want to show this 0. Everybody agree with that? Now here's the real pain a la Tushy on this one. The pain is, well, can somebody identify the pain? Somebody tell me what I'm feeling.
Like my pain is that X might not be a tensor, it might be a sum of tensors.
Oh, yeah. I'm feeling some pain on that. That's the big problem, right? Is number one, this X might be just this huge sum of tensors, right? Confusing. And here's another problem. Even if it's a single tensor, how do you know whether it's 0 or not? Right? Remember our earlier confusion with the Z2 was one tensor 1, is that the 0 tensor? I don't know. However, I think that we can do this in the following sense. Let us, so Eric, let's write that down because for sure this could be a problem. X, what do I know about X? I know it's an element of A tensor R, so I can do this. So far, that's the best I can do. Right, it's a sum of tensors. And I hope you guys, my notation suggested to you, the A's are in A and the R's are in R. Right? Okay, so does anybody see a way that I can move forward? you know, there's something very special. You know, I didn't just tensor A with B, I tensored it over R with R. This allows me to do something. You guys still do this?
Changing R to the A comes
Ah.
R1 is equals to R1 and comes to 1.
Okay, so I've got that. Right, and of course, I wrote that out suggestively so that you all can see what's going on, but actually, the left part of all these single tensors is just an element of A, right? Now, what else can I do? That's right. Notice I have the same thing in the second coordinate all the time, so basically, I can just, I mean, I can treat that like an accordion, right? Inductively, I collapse that all. Everybody okay with it? So we have gotten over the first hump in the following sense, and let me write this way. Every element, so this is an important observation. Every element of actually. Everything can be written in that form. It's fine. This is useful. So let me reformulate. And let's let my diagram help me out here. Now, what do we know? This is in the kernel. So this goes to G bar of A tensor 1, which is 0. Right? Still not much of a clue until I use the diagram. Notice A tensor 1 conveniently comes from the ordered pair A comma 1. Right. And this diagram has to commute. So when I go here and here, it's the same thing as going here. And what do I get when I go from here to here? 1 times A, which equals A, which equals 0. So G bar of A tensor 1 is equal to G of A comma 1, which is A, which is 0. So A tensor 1 equals 0 and G bar 1 of 1. Because since A is 0, 0 tensor 1 is 0. So there, not only do we use the fact, we sort of double use the fact in a certain sense that everything can be written as a single tensor. Okay, any questions? Okay, so let me give you this is another kind of dual relation between Hom and the tensor product. Do y'all remember how Hom was left exact? Right? Talk about that a little bit. So here's the theorem. 6.8. Tensor product's actually a little easier. Start with this. Yes. If is exact. So this is like contravariant Hom, right? Image of F is kernel of G and G is onto, but A may not be 1-to-1. Then so is and this is F tensor, the identity function on D, and this is G tensor, the identity function on D. So this is the induced F and the induced G, or the match induced by F and G tensor. Notice that notice that this is, of course, the map. That's what it does is it takes a tensor A tensor D to F of A tensor D, and this takes B tensor D to G of B tensor D. Okay, I think I can probably pound out 2/3 of this really quick, and we'll probably have to come back to the rest of it tomorrow. And I'll give you an example next time too, but you might think, see if you can think of an example. So what this says is this is right exact. So this tends to favor the onto, right, as opposed to Hom that favors 1-to-1. So what this means, it seems like, is if you have a 1-to-1 map, this induced map on the tensor product is probably not always 1-to-1. Sometimes it is, sometimes it isn't. See if you can think of an example where it's not. There's also going to be a companion theorem to this too, as you might guess. If this is split exact, then the tensor product is split exact as well. So let me do a couple of things. Let me get the easier details out of the way. Notice G tensor 1D is on to. Okay, so how are we going to do this? Well, note that C tensor D is generated by tensors of the form little c tensor little d, with C and C even. So everything in C tensor D is a sum of these little tensors like this, and each C in C is well, C for all, let's say C and C, there exists B and B such that G of B is equal to C. Right. Therefore, D tensor 1 of B tensor D equals G of B tensor D, which is C tensor D. So every C tensor D is in the image of G bar tensor 1. So G bar tensor 1D is equal to C tensor. Because this statement says that every generator is in the image. And so since you've got all the generators in the image, that means that C tensor D is contained in the image, and so it has to be equality. See if you can check. Also, since when you do G, you get the zero function. Then when you do F tensor 1D, composed with G tensor, do F then G, this is the zero function tensor, the identity of D, which is zero. So the image F tensor 1 contained in the kernel of G tensor 1. Okay, any questions on that? Questions? Okay, so this links the kernel is containing the image for next time. I hope y'all have a good weekend. Think about coming to Mac Club if you got time, and otherwise, we'll see you on Monday.